Okay, so last time we talked about rational functions on projective varieties, and we saw last time that the set of rational functions on projective variety is a field and is given by these guys. Yeah, so Kx is f over g, where f and g are elements of the homogeneous coordinate ring kx naught to xn mod ix, and they are of the same degree. So f is let's say capital F mod ix, and so f and g, one could write it as capital F mod ix and capital G mod ix respectively, such that degree of f and degree of g in kx naught to xn is same. But in fact, one can give a definition of degree of little f little g as well. So I'll talk about it in a bit. So last time the bijection was in the class. I sort of wrote 3-4 lines, but I said, okay, I'll either assign this as a homework um, or I'll write down the details. So I wrote it down in the notes, the details. So it's not. So I thought it could be done in a small box, but it requires a little more space. But the idea is very simple. Yeah. So maybe you can go through that. Yeah. Basically rational functions, as we have defined, is defined up to an is a function from some open subset of x to k, and we should think of rational function as two rational functions should be same if they agree on a non-empty open subset. Yeah. And remember, any non-empty open subset of a variety is dense. So with that in mind, you can sort of show that every rational function corresponds to some, gives you something like a fraction like this. And say two rational function gives you the same fraction, then the two rational function agree on an open dense set. And conversely, if two fraction, and if you take f1 f over g and f prime over g prime, so first of all, f over g does define a rational function on x, and if f over g and f prime over g prime define the same rational function, then one can show that f over g is same as f prime over g prime as an element of this field. Yeah, so that's what our cute. Okay. Also, last time we saw, so last time we saw that and that the and this this ring f such that f is a rational function and is regular at P is a local ring with maximal ideal M. Which is this thing, yes, and this proof is essentially the same proof as in the affine case. Yeah? So you first show that this set is indeed a subring of the field of rational function, and then you show that anything which you take outside M is invertible. Yeah, and also observe that M is indeed an ideal. So that proves that this has to be a local ring with maximal ideals. Okay. And so last and we ended with this. So I made the statement that f is a rational function on a projective variety x, such that f is regular at all points. So remember, regular at P. Okay, so we defined what regular at P means. So regular a rational function of the form f over g is regular at P if you can find a rational function from x to k is regular at P if you can find f and g such that f is equal to f over g and gp is not equal to 0. Yeah. If a rational function is regular at all points of a projective variety, then it must be constant. Yeah. So I didn't give you the proof for arbitrary projective variety. I gave you a proof for Pn. Okay, so we showed that if f is a regular function on Pn, then it must be constant. So it is true for general projective variety, but the proof maybe there is a elementary proof using Hilbert-Nernst and something, but it will require a bit more. So there is a proof using morphisms. Yeah. So basically a map from projective variety to any variety is closed. So is a closed map in the sense of topology. That means every closed subset goes to a closed subset, and from there it somehow follows. But that proof, yeah. So I mean, when you nail it down completely, it is sort of elementary. But if I have to do that chasing around, then it will become a longish proof. Put in so maybe there is a maybe if one decodes it, one can get a direct proof, but yeah, so I'll see if there is a direct proof with some steps, then maybe I can try to phrase it as a homework and give the steps so that you can do it. Otherwise one has to, maybe you can take this on faith, but maybe if you do a second course in algebraic geometry, you'll know that you'll see this result. Master's course in algebra, that any rational function on any rational function which is regular on a whole of on every point of a projective variety must be a constant. Okay. But for Pn we anyway saw the proof. Yeah. So we didn't do any much examples. So maybe I thought I'll start with an example today. Yeah. So suppose x is Pn. Yeah. So what is an example of a rational function on Pn? So Pn, we know what the homogeneous coordinate ring look like. Yeah. So x equals Pn, then then homogeneous coordinate ring is just the polynomial ring, yeah, kx not to xn. So if you think, so this is how we define Pn, yeah. So you can think of it, yeah, so we also talked about points in Pn and so on. So they are sort of lines passing through origin in an+1. So that corresponds to homogeneous maximal ideals of this ring. Yeah. So what are rational functions in this? So you have to take a function to homogeneous function of the same degree and take its ratio. So for instance, x0 over x1 is a rational function on Pn. Yeah. And where is it defined? So it is defined on locus where x1 is non-zero. Yeah. So on u1 equals x1 not equal to 0 locus. Yeah. So this was our notation for u1. So it does x0 over x1 does define. So u1 to k you get a map. Yeah. So if you have a so how does the map go? So let's just so you get a map from u1 to k. So a typical element of u1 looks like a0 a1 up to an. Yeah, with where we assume a1 is non-zero. So this has to go to a0 over a1. Yeah, so that is the map. This is a rational function from from Pn to this, which is well defined on U1. But something like x naught is not a rational function. So here note that if you change the way the definition is, if you take a different representative of this point a naught a1 an, the map won't change, because any two represent a naught a1 up to an is same as b naught b1 up to bn if bi is a scalar multiple of ai, yeah, so by the same scalar. So if bi is lambda times ai for all I, and then of course the lambdas in the numerator and denominator will cancel out, and you get the same expression. But something like x naught is not a rational function. Yeah, so x naught is an element of the fraction field of this polynomial ring in n+1 variable, but it's not a rational function on Pn. Yeah, so last time I told you that this is a field, but it is strictly smaller than the fraction field of this guy. Yeah, so I mean. Unless in some trivial cases, yeah. So if x is a point, then maybe they are the same. No, even then, yeah. So it's strictly smaller, yeah. So kx is strictly smaller than this. So for instance, x naught is in the fraction field of this guy. Here ix is 0, so the fraction field is just kx naught to xn, round bracket. But x naught is not is not a rational function. Yeah, so you do get something strictly smaller. Okay, and so I mentioned this and assigned this as a homework. So so in fact, if x is contained in Pn, projective variety, and U0 is contained in Pn given by x naught not equal to 0, then the rational so U naught intersection x we know is an affine variety, yeah. And if U naught intersection x is non-empty, then it is an affine open, a non-empty affine open subset, yeah. And we know how to, so there is this dehomogenization process which will give us which will tell us how to think of this as a affine variety. And then the field of rational function of U naught intersection x is same as field of rational function on x. Yeah, so maybe I'll just put it as an isomorphism. Yeah, but this isomorphism is natural. So I wanted to do this in a particular. So I wanted to discuss a particular example. So we will see what is happening in that example, and then maybe the same idea you can use to prove this. Yeah. So this will be homework for the upcoming week. Okay. So so let x be in P2. Be given by something like this. So this is so I did make some change here. I don't know why it's not appearing here. Yeah, so I did change. I didn't change here. So this the reason I changed. So if I take 0 set of this, what's the problem? Is x a projective variety? Is 0 set of this a variety? Projective variety?
Yes, because it's homogeneous.
So what is the condition for something to be projective variety? It should be 0 set of a homogeneous polynomial. That's it.
It is not a prime ideal, right?
It should be a prime ideal as well. The ideal generated by this should be a prime. Is that a prime ideal?
No, it's not.
It's not a prime. Yes, because you see x1 is a factor. Yeah, so that was the problem. So I'll just change this. I did change in the rest of the part, but I didn't change here. So x2 square. Now this is okay. Yeah. So so this will be so we'll see in the process that this is a variety, but now it's sort of believable. Yeah. So and that it is a prime ideal. Okay. So let's look at the homogeneous coordinate ring of X. So how what is the homogeneous coordinate ring? Is it's polynomial ring in three variables modulo this ideal generated by this guy. So I haven't changed here as well. Let's just x2 square. Okay. Okay. So of course you can think of this as the usual ring and so on, but I want so like in I want to write it down as direct sum of some degree 0 piece, degree 1 piece, and so on. Yeah. So so this since we are modding out by a homogeneous polynomial, we can do that. Yeah. So we'll get some. So in other words, there is a degree on this. So of course there is a degree on just the polynomial ring. So there is a degree 0 piece, degree 1 piece. So same thing happens if you mod out by a homogeneous ideal as well. Yeah. So you can write, so of course this ring, you can write it as in degree 0 piece you have k, in degree 1 piece you will have kx0, kx1, kx2, and similarly degree 2 terms will be there. So that doesn't get to, so you write it as k vector space, direct sum of k vector space. Forget about the multiplication structure for now.
It's a graded ring, right?
Yeah, it is a graded ring. So I'm just trying to say what it means. Yeah. So what does a graded ring mean? So you can write it as direct sum of a0, a1, a2, a3, such that a0 is a ring. So a0 in our case, so a is a graded ring if you can write it as direct sum of a0, a1, a2, a3. So for instance, here a0 is k, and k is a field. Yeah, so everything is fine. A1 is basically should be an A0 module. So here everything should be a K vector space. So of course this is, you are looking at degree 1 pieces. So they are generated by these three, and degree 2 terms. Similarly, you'll have, so there are certain number of degree 2 terms, right? How many are there? X0 square, X1 square, X2 square, and then the mixed terms. Okay, so I guess 3 mixed terms. So there are 6 dimensional degree 2 terms, and then you have to do degree 3 terms. So that will be whatever dimensional it is. Yeah. So but degree 3 terms also contain. So if you think of it as a vector space, then it contains this as a subspace, a scalar, any scalar times a multiple of this homogeneous polynomial. That's a subspace. Yeah. So so you can go mod that subspace, and that will be the first place where this ring will differ from the polynomial ring in degrees. Yeah, and then so the point is this ideal also has so this, if you have the point is, if I is a since this is a homogeneous ideal, I, you can write it as I0 plus I1 plus I2. Yeah, so maybe this is what I should have written on this side. So note I contained in kx not 2xn homogeneous ideal. Then so we have proved this. I'm not writing something which is we can write it as I is I0. So you intersect with degree 0 piece. So if I is a proper ideal, I0 is going to be 0. Degree 1 pieces, you intersect it with degree 1 pieces, you get I1 and so on. Can you see my screen? Hello, are you guys with me?
No, we can't.
Oh, so it just went off, right? Okay.
Yeah, just.
So something went wrong. Yeah. Okay. Good. So you can write it as I1 and so on. Uh, so of course the first few might be zero if I has I may not have any degree zero piece if I is a proper ideal. It may not. I mean if it may not have any degree one piece if in for instance if I is an ideal of this kind, then it doesn't have any degree one piece, degree two piece. So R this kx not to xn, and of course kx not to xn also you can write it as k plus so maybe I degree one pieces and so on. Yeah, so maybe I'll write it as yeah, k plus r1. So every yeah, every degree one polynomial, homogeneous degree one polynomial, and 0, and so on, R2 and so on. So this is how it will look like. Then and then this ring k x naught to xn is just mod I is as we know is just um, um, k mod I0 plus R1 mod I1 and so on. Rn mod in general. Yeah, Rd mod it, and is something else. Yeah, so this is how this will look like. Yeah, so now you can see what a degree of an element is. So any element in this ring is going to lie. Is some of these kind of terms. So if an element in Rd mod Id is said to be of degree D. Yeah, and is said to be homogeneous of degree D. Yeah, and so on. So every element in this ring you can write it as uniquely as sum of homogeneous elements of various degrees. Okay. And it's a graded ring means that if you multiply, so you say A is a graded ring if you can write it as A0 plus A1 plus A2 and so on, where A0 is a ring, AI is a A0 module for I greater equals 0. And if you and the multiplication, so if you multiply an element in AI and an element in AJ, then it should land in AI plus J. Yeah. And that is what you so if these three happens, then you say that is a graded ring. Yeah, so in that sense, this is a graded ring. So we know that the field of rational function on X is f over G, where f and G are elements of this homogeneous polynomial ring, such that degree f is equal to degree G in this homogeneous coordinate ring, and so f and G are here homogeneous. Yeah, so homogeneous in this sense, that homogeneous in this graded ring, and we want D to be non-zero. So that is the way we want to think about field of rational function. Okay. So that is how this is to be thought of as well. Yeah, where did it go? Yeah, so this is how. So f is little f is capital F mod Ix, and G is capital G mod Ix, and f and G are homogeneous implies little f and little g will be homogeneous. Conversely, if little f and if little g is homogeneous in that sense, then you can find f and g such that this happens. Yeah, so I haven't really cooked up a new definition. It agrees with the earlier one. Yeah. So now we want to look at some affine piece. Yeah, so affine piece where x naught is not equal to 0. Yeah. So what we do is look at declare x1 So this in this affine piece we'll have coordinates x1 and x2. So little x1 will be capital X1 over x0, and little x2 is capital x2 over x0. So now if we take a rational function on x, so it's of the form f over g, and say degree f is d, so degree g is also d, then f over g we can think of it as also as f over x naught power d bar, and so image of x naught in this quotient ring k x naught to xn mod the ideal, and also times x naught power d bar over g. Note that x naught does not belong to this this ideal. Yeah, so dividing by x naught power d bar is non-zero in this homogeneous coordinate ring, so there is no problem. Yeah. And if you think about what this does, so you know f is of degree d. So if you divide by x naught power d bar, then you know you are sort of so f is sorry. So f is going to look like some homogeneous polynomial in three variables x naught, x1, x2 of degree d, and you are dividing by x naught power d bar. Yeah. So it will become a function in capital X1 over x naught and capital X2 over x naught, and some x naughts will get cancelled. Yeah. So it will become something like that. So in fact, this becomes f of 1 x1 bar comma x2 bar. Yeah. And similarly, g will become 1 x1 bar comma x2 bar, where f yeah. So maybe I should write it this way. Yeah, so put bars here. Yeah. So if we had taken some representative of little f, capital F, then it will be in without bars, but we are working here. So this guy is actually in k x1 over x naught and x2 over x naught modulo. So we are just dividing everything by so now we are writing in terms of x1 and x2. Yeah. So it becomes an element of k x1 over x naught and x2 over x naught, and this homogeneous polynomial. So if you divide by x1 x, so this is how we did the dehomogenization as well. So you divide by x naught power 3, yeah, and you get x1 over x naught plus x1 x1 over x naught square times x2 over x naught, and then x naught x2 square over x naught square. Yeah. So the f and g are elements of this polynomial. So you can think of this ratio as element of this as a ratio of two elements in this ring, and this is precisely the dehomogenization. So and this is the coordinate ring of let's say u0 intersection x, where u0 is x0 not equal to 0 in P2. Okay. So and then we already saw that u0 is given by dehomogenization of this ideal ideal of definition of this variety. Yeah. And then the rational function, if you want to compare rational function, you do these kind of operations. Yeah. So I'll let you make this precise in using in this homework problem which I've assigned. Any questions or comments? Okay, so let me get to morphisms of varieties. Okay, so a map. So for affine varieties, we said that a morphism of variety is a morphism defined by polynomials. Yeah. So we realized that is sort of so you collect certain regular functions, and that gives you sort of a morphism. But we know that for projective variety, regular functions are very rigid. I mean, they are constants. So that won't work. So but we also know that every projective variety can be sort of covered by affine varieties. Yeah. So using this U0, U1, and so on. So we'll use that to define morphisms between varieties. Yeah. So phi from X to Y is a morphism between varieties. So X could be projective, Y could be affine. And we will define any variety to be an open subset of a projective variety for now. Yeah. So X could be some open subset of a non-empty open subset of a projective variety. So in literature, these are called quasi-projective varieties. So there are something slightly more general than quasi-projective varieties as well, which maybe you will see it in the next course if you take it. So for instance, affine varieties are quasi-projective varieties, right? Because you can any affine variety, you can think of it as you can embed it in AN, and you can complete it to P, and you can think of it as a close. You can take its closure in Pn. So it's an open subset of projective variety. Yeah. So quasi-projective varieties cover affine varieties, and open non-empty open subsets of affine varieties are also quasi-projective varieties. Yeah. So it covers everything. So a map phi from X to Y between varieties said to be a morphism if there exists an affine open cover Ui of X. So that means a union of Ui's is whole of X, and Ui's are all affine open subsets of X, and affine open cover Vi of Y, such that phi Ui is phi when you apply to Ui. So phi, remember, is a function. Yeah. So phi of Ui is contained in Vi, and phi restricted to Ui from Ui to Vi is a morphism of affine varieties. Yeah. So both Ui and Vi are affine. So then we can ask phi to be a morphism of affine varieties. Then, so if this happens, then we say that phi is a morphism of varieties. So there are other equivalent definitions. So maybe I should just point this out here itself. So one equivalent one is this. So so another way to say is that for all p point P in X, so let's call, okay, we are using capital P, so let's just do it. So for all points P in X, there exist open sets, open, affine, subsets U in X and V in Y. So both U and V are affine open, such that P belongs to U, phi P belongs to, phi P will be an element of Y, so it should belong to actually V, and U and phi of U is contained in, yeah, so maybe, yeah, so phi restricted to U is a morphism. So I can write it this way. Phi restricted to U from U to V is a morphism of affine variety. So these two look somewhat similar, and hence so actually they are the same notion. So locally at each point you can realize phi as a morphism of a fine variety. So there is a fine open cover such or in other words you can. So so this the original definition implies this is clear, and even the other way is okay, but that requires maybe some argument. Okay. So this is what morphisms of varieties look like. Yeah. So maybe let's see some example of morphisms of projective varieties. Yeah. So let's start with something. Yeah. So maybe even yeah. So maybe yeah. So maybe I'll come to this example, but maybe something even more elementary. Yeah. First. So for instance, I want to give a map from P1 to P1. Yeah. So P1 elements of P1 looks like A0, A1, class of A0, A1, and both A0 and A1 shouldn't be 0. So I want to send it to pair. Yeah. So of course I can send it to A1, A0. Yeah. So and then you can ask whether this is a morphism of variety or not. Yeah. Or I can send it to A0, A1 goes to A0 plus A1, comma. So I, or maybe maybe A1, something like this. But so let's write down some candidates and check whether they are morphisms or varieties or not. So A0, A1 goes to maybe A0, A1 and A1, something like this. Yeah. So so maybe this let's try this first one. Yeah, and then we'll see second and third. So first one, if we just change A0, A1 to A1, A0, is this a morphism of varieties in this sense? Yeah. So of course we have this P1. We can think of it as U0 union U1. Yeah, where U0 is x0 not equal to 0 and U1 is x1 not equal to 0. So these are a fine open subset of P1. Both are isomorphic to A1. And P1 also you can, and the other P1, maybe we take V0 union V1. Yeah, so unfortunately we have taken both as P1, but maybe, yeah, but hopefully it won't be a confusion, and there won't be a confusion. Yeah. So this is the U0 covers the domain, and U's cover the domain and V's cover the range. Okay. So now what is this map on U0? So what is phi restricted to U0? So U0 U0 means A0 should be non-zero. Yeah. So where does it send? A0 is non-zero, so it sends A0 A1 to A1 A0. Yeah. So first of all, this map is well defined. So A1 A0 both, if both of them are 0, then of course A0 A1 is also 0. So that point doesn't lie in P1. So that map is okay. But here, okay. So sorry. So what I want to say is that phi of U0, what is the range of phi of U0? phi of u0. So a0 is non-zero, so that tells us that phi of u, so v1 is given by second coordinate being non-zero. Yeah, so that tells you that phi of u0 is equal to v1. Phi of u1 is equal to v0. Yeah, so that is okay. And what is the map when I restrict to u0? Phi restricted to u0 from u0 to v1. What is the map? So it sends a0 a1 to a1 a0. Yeah, but I want to really think of u0 as a affine line. Yeah, and how do I think of u0 as a affine line? So a0 is non-zero. Yeah, so the way to think of u0 as a affine line is 1 comma a1 over a0. Yeah, so this point is same as this point in the projective space, and then I can think of u0 as an affine line. Yeah, it's just any element of k. Yeah, so this can depending on what a1 is, it can become any element of k. So this point goes to I guess I can write it as a1 over a0 comma 1. Yeah. So this v1 means the second coordinate is non-zero. So this is how we think of v1 as a1. So this is in fact isomorphism. Yeah, a1 over a0 goes to a1 over a0. So phi is indeed morphism. Phi restricted to u0 is a morphism of varieties. In fact, it's an isomorphism of a1 to itself. And similarly, the other way. Yeah, and you can check that this happens even for 2. Yeah, so for 2 also, u0 will go to where will u0 go to? A0 should be non-zero. So u0 will yeah. So okay. So for at least u1 will go to v1 the way it is, and you can check that u0 will also go to so a0 is non-zero. Yeah, so a0 is non-zero. So is it contained in v? Yeah, so it should be contained in the first quadrant being yeah. So okay. So maybe let's just work this out. Yeah. So um, so now this map phi is a0 a1 goes to a0 plus a1 a2 comma a1. Yeah, so this is the map, and u0 which is the locus where a0 is non-zero. So at least so you check that at least phi of u1 is contained is contained in v1. So if a1 is non-zero, then of course the second quadrant is non-zero. But at phi of u0, so I just have to take some affine open. I don't have to. It need not be the standard affine open. Yeah. So this is contained in v0 minus So I'll just remove both the pieces. Yeah. So uh, so uh, so maybe P1 minus A0 equals 0 and x0 equals 0 and x1 equals 0. Yeah, so if I remove both of them, then certainly this is okay. Yeah. Then the image, or locally you can just check that this is going to be give you a and then yeah, but the other thing one has to check is that it is indeed giving you a morphism of varieties. Yeah. So what does it look like in these affine coordinates? So when a1 is non-zero, it is so if a1 is non-zero, this a0 over a0 a1 is same as a0 over a1 comma 1, and this map sends it to um, um, a0 a0 plus a1. So I'm dividing by a1. Yeah, so a0 plus a1 over a1 comma 1. Yeah, so this is what the map will send it. I mean, it's the same point, but I want to look at it as a point here. So in V1, the 2 points are same in the respective P1s, and but what it sends it, what it does is this point is same as a0 over a1 plus 1 comma 1. Yeah. So in this case, phi restricted to u0 from a1 to a1 is sending some a0 over a1 to a0 over a1 plus 1. So alpha goes to alpha plus 1. So of course, this is given by a polynomial. So it is a linear map. And even if you do it in the other way. So if you look at the other chart, so so this was U1, phi restricted to U0. Then this map is, so this point is 1 comma A1 over A0. And this point will go to this point, but I want to now divide by a0, yeah, and see what yeah, so this actually here it goes to a0 plus a1 over comma a1, yeah, but I want to think of it as element of some yeah, some open set. Yeah, so I may have to cover it with more open sets, I guess. But maybe I'll keep it at to V0. Let's see what happens. Yeah, so maybe this is okay. So I'll just keep it as V0. So this how do I write it in a more reasonable way?
So why phi u0 is contained in v0? A0 plus 1 can be 0.
A0 is not 0, right? But A0 plus A1 can be 0. Yeah. So I'll have to make sure that A0 plus 0 is also not, A0 plus A1 is also, so I should take smaller, so I should cover the domain by smaller guys, yeah, then it will be okay. So I want to make sure that A0 plus A1 is also non-zero. Okay, so you have to, yes, but, okay, so,
X naught plus not equal to 0 if you use that.
say that again.
X naught plus x1 is not equal to 0.
Maybe, yeah, so maybe that is the homogeneous, that is what I should take, yeah. So that will also, those two will also cover, yeah. So instead of taking u0, x not equals to is 0, x not equal to 0, I should take, yeah, so maybe u0 is given by x naught plus, so maybe call it u0 tilde, yeah, because u0 we are using for that not equal to 0, yeah. So if you consider this as our open set, so this is also an open set because x naught plus x1 equals 0 defines a line in P2, and you are just look a closed subset in P2, so its complement is on this, and then phi of u0 tilde does lie in v0, yeah, where the first component is non-zero by definition, yeah. So now, but what is the map? So this I want to write it as something in terms of A1 over A0. Yeah. So but let's just divide by A0. Let's see what we get. Yeah. So what we get is 1 plus A1 over A0, comma A1 over A0. Yeah. But this is so this is also yeah, so this, I mean, in this domain also, it should be a morphism of varieties, but so, okay, so this point is same as, it's also same as 1 comma, so I really want to think of it as a point in on V1, yeah, so I'll just, this point is same as A1 over A0 plus A1, yeah. Hopefully it won't matter, and this point is 1 so now it is a point in V1, and I'll think of it as um, Yeah. Yeah, so yeah, this is okay. So this I can write it as A0 plus A1 over A0 plus A1 plus minus A0 over, that doesn't help, yeah. I want to write it in terms of A1 over A0. So let's try to write it in terms of A1 over A0. Okay, so um, so divide both numerator and denominator by A0. A0 is non-zero, yeah, so we can do that. So this is A1 over A0 over 1 plus A1 over A0. Okay. So the map at this level is so phi restricted to u naught tilde is sends the map from this A1 as we think of it as u naught tilde is we are removing 1 point from P1, yeah, so it's still A naught is sort of what am I doing? No, so u naught tilde is not of this form, yeah, so that is the problem. The map is this, but A naught may be 0. So we are in the domain where A naught plus A1 is non-zero. Yeah, so pardon me. So this is not right. So let's just try to redo this. So phi restricted to u naught tilde since A naught A naught A1 to A naught plus A1 comma A1, and in u naught tilde A naught plus A1 is non-zero. Yeah, so we can divide by A naught plus A1 and get something in B1 hopefully. Yeah, so this is this point is same as A naught over A naught plus A1 comma A1 over A naught plus A1 and so this I mean dividing by some same number doesn't change the point, and this point is 1 comma A1 over A naught plus A1. Yeah, but I should think of yeah, so u naught tilde yeah, so u naught tilde is isomorphic to the affine line, but it's not yeah, so one has to think of how you identify it with A1, yeah, in P2. So
Tilde can be again covered, but that will be complicated.
yeah,
And tilde you can again cover it by A naught not equal to 0.
yeah, but yeah. But I want to do it at one go. So maybe that's and that's why it's probably better to use the other definition. Given any point, you can find an open subset. And then see, the point is we have more or less for all points we have done it. Alpha goes to alpha plus 1 is the map. Only one point which is missing is the point at infinity. If you think in terms of this u1, so there's only there's only one point missing, and in that neighborhood it will be given by so that again by some polynomial. Yeah. So which will be something like alpha goes to alpha plus 1, but yeah, so yeah, so there should be a direct, I mean, this is the direct way of doing it, and there is something which, so one has to identify this U0 tilde with A1 appropriately. Yeah, so maybe let's just try, let me try one more time. Yeah, alpha belongs to U0 tilde. Then okay. Yeah, so this point, yeah, so one has to do cases. So if A0 is not equal to 0, then this point is same as 1 comma A1 over A0. Yeah. And so one has to do various cases. So in that case, this map, this phi is phi is given by this sense. Yeah, so maybe this is how. So if A1 is not equal to 0, the map is given by alpha goes to alpha plus 1. If A0 is not equal to 0, this is A1 over A0. And so that is the only point one has to worry about, but is captured in this chart. And yeah, so then this, if A0 is not equal to 0, then this, the right hand point is same as 1 A1 over A0 over 1 plus A1 over A0. Yeah. So if A0 is not equal to 0, this point goes to this point, which is alpha goes to alpha over 1 plus alpha. Yeah. So so this doesn't make sense if alpha is minus 1. Yeah, but so alpha, yeah, so if A1 over A0 equals minus 1, that means, yeah, so yeah, so this works out. Yeah, so this is the map. Yeah. So phi is this map, and so I wanted to show that this is a so this is certainly given by polynomials. Alpha goes to alpha over 1 plus alpha. So it won't make sense if A1 over A0 is equal to minus 1. Yeah, so if alpha is minus 1, but this implies that A0 plus A1 equals 0. But that doesn't. But such a point. But this intersection U0 tilde is empty. Yeah. So such a point does not belong to U0 tilde. Yeah. So phi restricted to U0 tilde is this map, and this of course is again given by polynomials in some sense. Yeah. So 1 plus alpha is never 0. So it. Um, so it. So it indeed is so the image of U0 tilde does lie in V0 tilde. Yeah, so it does lie in V0. Yeah, so phi tilde of U0 tilde is contained in V0, yeah, because the denominator doesn't vanish here. Yeah, so the image is okay. Yeah, it's well defined. Okay. So I hope this is clear. So maybe so I've gone over much, but unfortunately I didn't do any other example. So maybe tomorrow. So okay, maybe I'll stop here. So so tomorrow I'll briefly discuss this. So this so the third one is missing. So this is not a morphism, not a morphism, not a morphism. So let me just tell you why, and then we will stop. Yeah. So note that I mean somehow this is not given by some homogeneous thing. Yeah. So yeah. So why? First of all, is this well defined? So if I take so for instance, if I take A1 to be uh, 0, then it goes to 0, 0. Yeah. So 1, 0 goes to 0, 0. So it's not even well defined the way map is written. But one can ask whether, I mean, but that's just one point. Yeah. So what if A1 is non-zero? Is this still so is this at least a rational map? So away from it may not be a morphism, but maybe it's defined on an open subset. But that is also not true. So the point is, this is not homogeneous. So A0, A1 is same as lambda A0, lambda A1. Yeah. But lambda A0, lambda A1 will go to, so this guy is going to go to A0, A1, comma A1. Yeah. And this guy is going to go to lambda square A0, A1, comma lambda A1. Yeah. So of course, these 2 points are not same because one is a lambda, so they are not scalar multiple of each other. Yeah. So this map is not even well defined. Yeah. So this is not even so you can't just assign something random. It may not give you a. So if you put homogeneous guys of the same degree, then it is okay. Yeah. So if you put A0, A1, and maybe yeah, so degree some other degree too. So A1 square, then this is okay. Yeah. So if you put A1 square, then this becomes lambda square A1 square. So then it becomes a morphism. But without a square, this is not a morphism of varieties. Okay. So next time we will see a few more examples of morphisms of projective varieties, and then maybe we'll stop, and Thursday you'll have a quiz.